My name is Dmitry Kiselev. I'm a scientist at Sberbank, and I work on recommendation system, context, and other models. I'll tell you about those models, why we need them, and how we can validate them. So, what is a recommender system? They solve the main problem connected to what a certain pattern in a certain situation should be recommended, what goods to show or content to show, to make them most likely to buy them or pay the most money to make it profitable for the company. As input data, we usually use a history of user interaction with different goods and a description or parameters of certain users and goods. Of course, we have a series of problems. For example, what if we have no history? What do we do if we add new items? These problems are frequent when we have dynamic content. New articles, new news, we don't know what to recommend. And there's no history for such news. Now, what do we do if historical data is changed dramatically? New context, for instance, you all know about COVID. You shouldn't recommend people traveling articles after COVID hit because they won't be able to do anything, right? So the first problem is called the cold start problem. The recommender model is very likely to fail to answer the question, what do we show to the user if we have new users or new goods, new items? The classic solution for such a problem is using models that consider the parameters of the user and the items. The last problem is connected to the degradation of the model. If a model has been used for a long time without learning, its performance can fall down. If there are lots of new items, we don't know what to do with them. And that brings us back to the previous problem. Or, like I said, COVID hit, situation changed, the model will react badly. We can sometimes reteach the models for them to show better quality and use more relevant data. However, there's another problem. The data that our systems collect are shifted. The users choose only what the recommender gives to them. Imagine there's a user who likes reading articles about sports. When the system gives them articles on sports only, they will react well to them, but we don't know if they're interested in anything else, like cars, or say, traveling. So, the system will only focus on sports articles, better and better every time, just no other topics. We can solve that by adding some random predictions, so that the user will react to them as well. Random is not really good, though. We need to be smart about it, right? And the solution to all these problems can be done by teaching online. We get historical data, because we'll teach the model on a real flow of users who leave feedback. Now, how do we do that? For instance, there's a classic approach, multi-armed bandits. They work on clickability or some other metrics, or money, for instance, earned from a client. And it says more than just, it does more than just saying what's relevant at the moment. It balances between exploration and exploitation. And it does it smartly. We can find what goods are better by measuring the intervals for new items that we don't know much at the moment. So with learning, we'll get better precision. It only works for additional items, and it doesn't consider the context for different users. So we need to do that too. We need to consider user information, items information, context information. Like I said, we don't really need a lot of historical data here because we adapt online, live, when we get feedback from users. When there's a new item, we start exploring it, if it's relevant to certain users or not, and then we find a group of features that will be good to work with. We also have a share of traffic that we explore, and we don't need to be afraid of touching upon certain context or choosing the wrong one. Okay, so now we know what to do, but we need to check if it actually works. There are two approaches: simulators, that gives you an opportunity to build an environment, simulate user behavior, how a real one would react to our work, and off-policy evaluation. That allows us to work with historical data and fight the bias and the shift that I mentioned previously. Simulators come aplenty. Google RecSys is the most popular, also Criteo, Recogym, and Facebook Reagent. We worked with RecSys because others weren't satisfactory in their functions, or just didn't work for us. As I said, they allowed to build an environment that describes how a user works and how users react to items. But when we know how they reacted, we can build a model, which means we don't need the system, we don't need the environment. We already have the model of their behavior, we already know how they will react to a certain item. Of course, it's hard to build these models, and it's not always meaningful because sometimes facts just spoil everything. So we use simple models that can answer questions like, can a model train at all? Or have we just produced a thing that just randomly shuffles things? Now, to understand that, does it really work? We have OFE. The first part is replay. Yahoo guys used it to assess their bandits and their news feeds. Netflix uses it too to assess the experiments in ranging for a certain user in the movie recommendations. Now let's imagine we have a set of historical data and an agent that should recommend something to a user. Now let's take a line from this data, knowing the parameters, the user, and that they liked a certain movie or a certain part of it. The problem is we're trying to validate an agent, and an agent can show data completely different from what the user actually liked, and that will mean that the model made a mistake. Actually, we just couldn't not make a mistake in this situation. That will create bias, which is bad. And the solution was pretty simple. Just find some points where there's no cross between the show and the recommendation of the model that we actually used. And it works really well. We have some parts of the article, original article, we have offline, online metrics and overall metrics that we got during the test. And we see some correlation here. It's pretty high. When the data we have is random, which is a problem, because it's very expensive to correct that, and we'll lose money on that. This problem can be solved with normalized importance sampling. So the task is that we know we have some data collected with a policy, a previous recommended system, and we have a different probability of showing certain items to certain users in a context. We know that our agent, with some probability, will show certain item. We know that the probability was different for this item earlier. If a new agent says that some unpopular items almost never shown should be more popular now, are going to be, we won't be able to assess it normally, because our sample is small. So we can give more weight to each such click. It's a rare thing, and we can normalize the weights compared to the previous set based on the prediction model. That allows to reduce it a lot. On the left, we see CTR, the clicks share against shows, and on the right you see the normalized CTR. You see that it's all very variable on the left, and there's no learning seen. On the right, you can see that the model is learning, and it's much smoother. So this reduces dispersion and allows to learn based on historical data. So both these approaches allow us to train the model on data gathered by the previous model system. Of course, we might not have a model at all, so Google proposes that we use their model, which will solve that problem, that task. You can use it as a normalizer. Now, we've learned to evaluate offline. Now, production. How does it work? You can check the base and compare the models. You can see regular A/B tests. Well, we can't see how our models work on we can check it in previous situations on a random agent. But when we work online, we can't do that anymore because it's expensive. A/B test will give us an understanding if it works better or worse than the previous model, at least. So fine, we launched the test, realized it works, launched it. After a while, we want to see, is it still learning? Do we still get any learning when we add new items? Or is it outdated now, like classic models sometimes do? In this situation, we can try to see the weights it learns, or if it's non-linear, we can check the average user parameters, recommendations for items. Now, if everything's good and done correctly, if the features are standardized, they can be higher or lower, then the weights for each dynamics will be positive or negative, but it will be stable. Now we're certain there's some learning, there's some dynamics. In case of item 10 here, second on the right, we see that this feature just doesn't affect the item. A similar situation to not learning at all. Now, conclusion. Reinforcement learning model or multi-handed bandits allow to solve classic problems for these systems. But that leads to another problem. How do we check if they're working at all? We have several options. We can use simulators. Helps us understand the model learn something. We can also just discard bad models at this stage. Then, how will it work in our reality? We can use replay to just iterate over historical data and normalize important sampling to remove the shift that was created when we worked on previously used policies, collecting data. Now we can also check the weight's dynamics to understand if there's any dynamics to a certain direction, which will help us understand what items, what user parameters should be given more priority. That's it. Thank you so much for your attention.